Hello everybody, welcome to the Independent Study Packet videos. In this video we will discuss piecewise and absolute value functions. Please follow along in your packet. Please take all notes and do all problems. The recommended due date for this portion of the video is July 17th. If the material in this video is going too fast or too slow, please remember that you have the ability to pause, rewind, or fast forward. A piecewise function is a function given in two or more pieces. Here is a function h of x that's given in two pieces. Basically, we're dealing with a quadratic when x is greater than -4. We're also dealing with a line when x is less than or equal to -4. For part 1, the directions are to graph each of the following piecewise functions. For number 1, we're going to graph h of x. We can do that by making a table of values for each piece. We'll start with the quadratic piece. It tells us into the quadratic piece we should plug in x values greater than -4. Here's a tip. Even though it says x is greater than -4, include -4 in your table anyway. Here are some more x values greater than -4. Now find the y values to obtain all of these points. Now we'll set up a table of values for our line. Remember, we're only dealing with a line for x values less than or equal to -4. So in our table, in the x column, include values that are less than or equal to -4. -4, -5, -6, -7 should do. And then find the y values. Now we will run an endpoint analysis. Notice in our quadratic piece, x is greater than -4. That means the point -4, -3 is not included in our quadratic. Notice that in our second piece, the line, x is less than or equal to -4. That means that the point -4, -3 is included in our line. We should also notice that our pieces connect at the point -4, -3. Finally, although -4, -3 is not included in our quadratic piece, it is included in our function as a whole. Now it's time to sketch our graph. First, set up your coordinate system and please label each slash mark on each axis. Plot the points in your quadratic piece. Notice that -4, -3 is not included in this piece. That's why I have a hole in the graph at the point -4, -3. Since this piece is a quadratic, we should make it look like a parabola. Now we'll plot the points in our second piece, the line. -4, -3 is included, so now we can actually include that point. Here are the rest of the points, and now we can sketch our line. We can label our function with an h. Since the pieces connect, this function is continuous. For now, continuous means that if I put my pen down on the paper, I can draw this entire function without picking up my pen. We should also notice that h of x is indeed a function because it passes the vertical line test. On to number 2. In number 2, f of x is a function given in 3 pieces. To graph this function, we'll set up a table of values for each piece. In the first piece, we're dealing with a quadratic function for x values greater than 3. Remember our tip to include 3 in our table. Then include some x values greater than 3 and find the y values to obtain these points. The second piece is a constant function where 0 is less than x and x is less than or equal to 3. Even though it says x is greater than 0, include 0 on our table anyway. All of the y values will be 5. For our third piece, we're dealing with a line when x is less than or equal to 0. So make sure when you're making your table, your x values are less than or equal to 0. Then find the y values to obtain these points. Now we can run our endpoint analysis. In our quadratic piece, since x is greater than 3, the point 3, 5 is not included in the quadratic. In our second piece, the constant piece, since x is greater than 0, the point 0, 5 is not included in that piece. but since x is less than or equal to 3, the point 35 is included. Notice that the quadratic piece and the constant piece both line up at the point 35. That means that the point 35 is included in the entirety of our function. Finally, in our third piece, the linear piece, since x is less than or equal to 0, the point 04 is included in our line. Now we can take all this information and make a graph. First, set up your coordinate axis and label each slash mark. Here are the points in our quadratic piece. Notice that at present the point 35 is not included, that's why there's a hole in the graph. Now form the parabola. Here are the points on our constant piece. At this time 35 is included, so we can fill in that hole. Connect the points to make our constant piece. Now for the points on our linear piece. The point 04 is included. Here are the rest of the points, and here is the linear piece. We can label the function with an F, and this function is not continuous. In tracing this function, we would have to pick up our pen right here. This is called a jump discontinuity. Finally, notice that f is indeed a function because it passes the vertical line test. Okay, you should now be able to complete number 3. Okay, moving on to part 2. Here is a definition. Let x be a real number. The absolute value of x is the distance x is from 0. Since absolute value is a distance, the absolute value of x is always positive. The absolute value of x is notated like this. The absolute value of 3 is 3 because 3 is 3 units away from 0. The absolute value of negative 4 is 4 because negative 4 is 4 units away from 0. Now it's time for an algebraic definition. The absolute value of x equals x if x is greater than or equal to 0. The absolute value of x is equal to the negative of x if x is less than 0. So consider the absolute value of 3. In this case, 3 is positive, so we're dealing with our first piece. According to our algebraic definition, in this case the absolute value of x is equal to x, so the absolute value of 3 is equal to 3. Now consider the absolute value of negative 4. Negative 4 is negative, so that means we're dealing with this piece, the second piece. In this case, according to our algebraic definition, the absolute value of x is equal to the negative of x. So the absolute value of negative 4 is equal to the negative of negative 4, which is 4. The directions say simplify each expression and state only an exact answer. To get the most out of these exercises, let's show our work by using the algebraic definition. Number 4, the absolute value of negative pi. Note that in this example x equals negative pi, so we are dealing with the second piece, this piece right here. In this case, the absolute value of x is equal to the negative of x. This means that the absolute value of negative pi is equal to the negative of negative pi, which is pi. Number 5, we're going to find the absolute value of the quantity pi minus 3. In this problem, x is equal to pi minus 3, which is positive. So here we're dealing with the first piece. In this case, the absolute value of x is equal to x. So the absolute value of pi minus 3 is equal to pi minus 3. Number 6, we'll find the absolute value of the quantity pi minus 5. In this example, x is equal to pi minus 5, which is negative. We're dealing with the second piece. In this case, the absolute value of x is equal to the negative of x. The absolute value of pi minus 5 is equal to the negative of pi minus 5. Distribute the negative to obtain negative pi plus 5. Please try out 7, 8, and 9. For these examples, it's helpful to remember that e is an irrational number, it's Euler's number, and it's approximately equal to 2.718. Okay, let's skip down to number 11. Rewrite each function without an absolute value symbol. Number 11, f of x equals the absolute value of the quantity 2 minus 5x. To write this function without an absolute value symbol, it's helpful to remember our definition of absolute value. Ding, 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 ding. And since we don't want these x's to confuse us, we'll think a little bit more abstractly. The absolute value of a is equal to a if a is greater than or equal to 0, and it's equal to the negative of a if a is less than 0. In this problem, a is equal to 2 minus 5x. So we should make our substitutions. F of x, which is the absolute value of 2 minus 5x, is equal to a if a is greater than or equal to 0, or it's equal to the negative of a if a is less than 0. Now we should solve these inequalities and distribute this negative. Subtract 2 from both sides, divide by negative 5, and obtain x is less than or equal to 2/5. Make sure we flip the symbol since we're dividing by a negative. We can do the same thing right here to get x is greater than 2/5. And now we can write our final answer. The absolute value of 2 minus 5x is equal to 2 minus 5x if x is less than or equal to 2/5, or it's equal to negative 2 plus 5x if x is greater than 2/5. We should notice that the absolute value function is a piecewise function. So therefore we can graph this function by making a table for each piece. For our first piece, we're dealing with the line 2 minus 5x when x is less than or equal to 2/5. So here's a table for that piece. For our second piece, we're dealing with the line negative 2 plus 5x when x is greater than 2/5. So here's the table for that piece. Also, notice that the pieces line up at the point 2/5, 0. So the point 2/5, 0 is included in our function. Finally, here is our graph of f. So using this information, please try numbers 10 and 12. Part 3. For this part, let a and b be real numbers. The distance between two numbers a and b is represented by the absolute value of a minus b. That's equal to the absolute value of b minus a. Here's a diagram to help our understanding. We can see that the distance between a and b is the absolute value of a minus b, and that's equivalent to the absolute value of b minus a. So over here, consider the real numbers 4 and 7. We know that the distance between 4 and 7 is 3 units. The absolute value of 4 minus 7 is equal to 3, and the absolute value of 7 minus 4 is equal to 3. So the distance between 4 and 7 can be represented by either of these two absolute value expressions. And finally, we should definitely make note of the minus sign in our definition. Okay, moving on to the examples. It says describe the meaning of each mathematical statement. Number 12, we're looking at the absolute value of the quantity x minus 4. Here, a is x and b is 4. So according to our definition, this expression represents the distance between x and 4. Number 13, the absolute value of the quantity y plus 8. First, make a note that this expression equals the absolute value of y minus negative 8. Now we see what the a and the b are. A is equal to y and b is equal to negative 8. So this represents the distance between y and negative 8. That is how we will deal with this plus sign. Number 14, the absolute value of x minus pi is greater than 6. In this problem, it is clear that a is equal to x and b is equal to pi. Therefore, this inequality represents that the distance between x and pi is greater than 6. Please use this information to complete 15, 16, and 17. In the examples below, the directions say to write each sentence as a mathematical statement. Number 18. The distance from x to 7 is 6. Mathematically, here is the distance from x to 7. That is equal to 6. Number 20. The distance from x to negative 5 is equal to 1. Mathematically, this represents the distance from x to negative 5. That distance is equal to 1. Therefore, the absolute value of x plus 5 equals 1. Please use this information to complete exercises 19, 21, 22, and 23. Part 4. Solving absolute value equations and inequalities. Notes. There are 3 rules we should study. Suppose the directions say solve for x. Number 1, we have the absolute value of x equals a. Our job is to find all x values whose distance from 0 is a units. We should note that this equation only makes sense if a is greater than or equal to 0. So let's think about this graphically. There are 2 x values that satisfy our requirement. One of them is a, because the distance from 0 to a is definitely a units. The other one is negative a, because the distance from negative a to 0 is a units. So now we have our rule for absolute value equations. If the absolute value of x equals a, that's equivalent to saying x equals negative a or x equals a. It's easy to check this rule algebraically. For x equals a, the absolute value of a is certainly equal to a, since a is greater than or equal to 0. For x equals negative a, the absolute value of negative a is certainly equal to a. Just for a quick example, suppose we're trying to solve the equation the absolute value of x equals 7. You can see that 7 or negative 7 will make this equation work. Therefore, our solution is x equals negative 7 or x equals 7. Moving on to Rule 2. We'll call this rule the conjunction rule, or the AND rule. Suppose we are trying to solve the inequality the absolute value of x is less than a. Our job is to find all the x values whose distance from 0 is less than a units. We should think about this graphically. Consider a and negative a. Both are a units away from 0. Now we will shade all of the x values whose distance from 0 is less than a units. We would shade on the quote-unquote inside. That means we're shading between negative a and a. Notice for any arbitrary x value that we choose in the shaded region, the distance from x to 0 is certainly less than a units. That is also true on this side as well. The distance from x2 to 0 is certainly less than a units. So we have our conjunction rule. The absolute value of x is less than a is equivalent to negative a is less than x and x is less than a. For a quick example, suppose we're trying to solve the inequality the absolute value of x is less than or equal to 7. We should immediately notice this as a conjunction, and therefore we can rewrite negative 7 is less than or equal to x and x is less than or equal to 7. You can notice the conjunction rule quickly by using this tip, less than and. Less than and. That little tip will only apply when your absolute value expression is on the left-hand side of the inequality, so be careful there. Lastly, rule number 3. We will call this the disjunction rule, or the OR rule. Suppose we are trying to solve the inequality the absolute value of x is greater than a. Our job is to find all of the x values whose distance from 0 is greater than a units. We can think about this graphically. Consider a and negative a. Both are a units away from 0. Now we will shade all of the x values whose distance from 0 is greater than a units. We should shade on the quote-unquote outside. Notice that for any arbitrary x value in the shaded area, the distance from x to 0 is certainly greater than a units. The same is true on this side as well. The distance between x2 and 0 is greater than a units. So now we have our rule. The absolute value of x is greater than a is equivalent to x is less than negative a or x is greater than a. So to solve the inequality, the absolute value of x is greater than 7, we need to use the disjunction rule or the or rule. We need to notice that quickly, and therefore we can solve the inequality. The solution is x is less than negative 7 or x is greater than 7. To recognize the or rule quickly, look for a greater than symbol. Greater or. Greater or. Greater or. Now that little tip will only work if the absolute value is on the left side of the inequality. When it comes to solving absolute value equations or inequalities, our strategy is this. Given an absolute value equation or inequality, we should use those three rules to rewrite it without an absolute value symbol. The equation that we obtain, we will be able to solve using our regular old techniques. Solve for x and sketch a graph of the solution set on the number line. Number 24. The distance from x to 10 is equal to 17. This is an absolute value equation. That means that x minus 10 can either be equal to 17 or x minus 10 can be equal to negative 17. So we will rewrite our absolute value equation without an absolute value symbol. X minus 10 equals 17 or x minus 10 equals negative 17. We obtain the solutions x equals 27 or x equals negative 7. Here is our graph of our solutions on the number line. Notice that we are only dealing with two solutions. Here is the graph of our solution set. Notice that our graph only contains 2 points, negative 7 and 27. So there is no shading here. Side conversation. If we were thinking strictly graphically, remember that this equation means the distance from x to 10 is equal to 17. So consider 10 on the number line. Our job was to find the x values whose distance from 10 is 17 units. 17 units to the right would get us 27. 17 units to the left would get us our negative 7. You could also check the equation algebraically by plugging in 27 and negative 7. Number 26, the absolute value of x plus 5 equals negative 9. That means that the distance between x and negative 5 is equal to negative 9. This equation has no solution because a distance cannot be negative 9. Now, if you didn't notice that, you may have incorrectly wrote that x plus 5 equals 9 or x plus 5 equals negative 9. From that, you would have obtained x equals 4 or x equals negative 14. But if you were to check your answers, you would see that in each case, if you plugged in the 4 or the negative 14, you would have gotten 9 and not negative 9. This equation has no solution. Number 29, the absolute value of 3x minus 4 equals the absolute value of 2x plus 13. In order to use our absolute value rules, we need to isolate our absolute value. That means that we want an absolute value expression on one side and a number on the other side. In order to get that, one thing we can do is divide the absolute value of 2x plus 13 from both sides. That way, over here on the right, you'll get 1. On the left, we can bring the two absolute values together to get the absolute value of 3x minus 4 divided by 2x plus 13. And now we can use our absolute value equation rule. This thing right here can either equal 1 or it can equal negative 1. Solve both equations to obtain the solutions x equals 17 or x equals negative 9/5. And here is a graph of our solution set. Number 31, the absolute value of 2x minus 3 is less than or equal to 5. Now we should write the inequality without an absolute value symbol, and we should use our conjunction rule or our AND rule to do this. Negative 5 is less than or equal to 2x minus 3, and 2x minus 3 is less than or equal to 5. Add 3 and divide by 2 to obtain our solution. Negative 1 is less than or equal to x, and x is less than or equal to 4. And here's the graph of our solution set on the number line. Here's another interesting way of thinking about this problem. It says that the distance from 2x to 3 is less than or equal to 5. Our goal would be to find all of the 2x values whose distance from 3 is less than or equal to 5 units. We could think entirely from a graphical standpoint. Consider 3. 8 is 5 units away from 3, and negative 2 is 5 units away from 3. The shaded region would be all of the 2x values whose distance from 3 is less than or equal to 5 units. That's precisely the inequality that we came up with in the middle of doing this problem. Number 32, the distance from 4 to x is greater than 5. Greater or we should use our disjunction rule or our OR rule to rewrite our absolute value inequality without an absolute value symbol. We will get 4 minus x is greater than 5, or 4 minus x is less than negative 5. We will get x is less than negative 1, or x is greater than 9. And here's the graph of that solution set on the number line. Side topic. Again, it's interesting to think entirely from a graphical standpoint. Our job is to find all of the x values whose distance from 4 is greater than 5. So here is 4. 5 units to the right is 9. 5 units to the left is negative 1. And here are all the x values whose distance from 4 is greater than 5 units. Number 33. 1 is less than or equal to the absolute value of x minus 4, and the absolute value of x minus 4 is less than 2. There are two absolute value inequalities that we have to solve right now. In the end, we will have to intersect our solutions. Over here, it'll be helpful to do a rewrite. We're dealing with the absolute value of x minus 4 is greater than or equal to 1. Greater or rewrite without an absolute value symbol. X minus 4 is greater than or equal to 1, or x minus 4 is less than or equal to negative 1. That means that we have x is greater than or equal to 5, or x is less than or equal to 3. Now we should work on this side. Less than and. We should rewrite without using an absolute value symbol, using the AND rule. Negative 2 is less than x minus 4, and x is less than 2. Add 4 to each section to obtain 2 is less than x, and x is less than 6. Remember, our final answer needs to be the intersection of these two sets. So now we should go to our number line. We have 2, 3, 5, and 6. Here is x is greater than or equal to 5, or x is less than or equal to 3. Here is 2 is less than x, and x is less than 6. 3 is in common. 2 is not. 5 is in common. 6 is not. All of these points are in common. So here is the intersection of the two sets. Our final answer is 2 is less than x, and x is less than or equal to 3, or 5 is less than or equal to x, and x is less than 6. It's fun to think about this problem like this. The distance from x to 4 is less than 2 and is greater than or equal to 1. That means that our goal is to find all of the x values whose distance from 4 is less than 2 and greater than or equal to 1. You can think graphically. 3 and 5 are both 1 unit away from 4. 2 and 6 are both 2 units away from 4. So here are all of the x values that are less than 2 units away from 4 and greater than or equal to 1 unit away from 4. Okay, so using this video, please complete the rest of the questions in part 1 of this packet, piecewise and absolute value functions.